Right now, a machine built in the 1970s is falling silent, 48 years into a journey that will not end when it dies. It is 25 billion kilometers from you. It is moving away at 61,000 kilometers an hour, and it is never coming back. In just a few short months from now, it will cross a threshold no human-built object in all of history has ever crossed before. A radio command sent from Earth will take a full 24 hours just to reach it. Say good morning on a Monday, and the answer arrives on Wednesday. This is Voyager 1, and its story is only beginning. Everything you think you know about this spacecraft, the Grand Tour, the pale blue dot, the golden record, is the prologue. What comes next stretches so far past human history that the numbers stop meaning anything. 10 trillion years, not a metaphor, an actual future waiting in the dark, and Voyager 1 is heading straight into it. Before it became a monument, it was a bet. NASA scientists in the early 1970s noticed something that happens only once every 176 years. Jupiter, Saturn, Uranus, and Neptune would all line up on the same side of the sun, close enough together that a single spacecraft could use each planet's gravity to slingshot toward the next one, skipping years of travel time with every flyby. Miss that window, and the next T-chance would not come until the 22nd century. So engineers built two nearly identical machines, Voyager 1 and Voyager 2, each one packed with cameras, spectrometers, magnetometers, and enough backup systems to survive a decade in deep space, even though nobody expected them to still be transmitting 50 years later. Voyager 2 launched first on August 2nd, 1977. Voyager 1 followed 16 days after on a faster trajectory that would let it reach Jupiter and Saturn first at the cost of skipping Uranus and Neptune entirely. That single trajectory decision, made in a control room decades before anyone reading this was born, is the reason Voyager 1 is now the farthest human-made object in existence, ahead of its own twin, ahead of every other spacecraft ever launched. Launched on September 5th, 1977, from Cape Canaveral, Voyager 1 was never supposed to matter this much, this long. Its job was simple by comparison. Fly past Jupiter, fly past Saturn, take pictures, measure fields, phone home. It did that job in under 4 years. Then something unusual happened. NASA did not turn it off. The spacecraft kept flying, kept working, kept transmitting, long after its official mission ended. Nobody planned for a 50-year spacecraft. Nobody built for it either, not really. The engineers of the 1970s were solving 1970s problems. How do you GT a probe past two gas giants using a once-in-a-176-year planetary alignment? They were not thinking about the year 2026, and yet here we are, and here it still is, older than most of the people reading a headline about it, drifting through a region of space that did not have an official name in astrophysics, until Voyager itself proved it existed. Right now, in 2026, Voyager 1 sits at roughly 170 astronomical units from the Sun. One astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. Multiply that by 170, and you get a number that stops feeling like distance and starts feeling like abstraction. 25.5 billion kilometers, almost 16 billion miles. It is moving at about 17 kilometers every single second, over 60,000 kilometers an hour, fast enough to cross the continental United States in about a minute. And it has been moving at that speed, uninterrupted, since a gravitational slingshot past Saturn in November 1980. No further course corrections, no engine burns to speed it up or slow it down, just momentum, pure and unbroken, carrying a piece of 1970s engineering deeper into the dark every second of every day. The power comes from 3 radioisotope thermoelectric generators, RTGs, devices that convert the heat of decaying plutonium-238 into electricity. There is no sunlight out here, astronomical units. Sunlight is roughly 30,000 times fainter than it is on Earth, far too weak to run a spacecraft. So Voyager 1 carries its own tiny nuclear furnace, a chunk of radioactive metal slowly falling apart, and turns that decay into the electricity that keeps the lights on, literally and figuratively, across interstellar space. The problem is that plutonium-238 has a half-life of about 87 years. It is not gone, but it is fading, and every year Voyager 1 has less power than the year before. NASA engineers say the spacecraft loses about 4 watts of usable power every single year. That does not sound like much until you realize the entire spacecraft now runs on approximately 3 watts, less power than an old refrigerator light bulb, less than a single string of Christmas lights, and dropping. That shrinking power budget has forced a decade of hard choices. One by one, instruments have gone dark. The cosmic ray subsystem, which spent decades tracking high-energy particles from the galaxy and the sun, was switched off in February 2025. The low-energy charged particle instrument, which helped scientists map the shape of interstellar space itself, was shut down in April 2026. As of right now, only two science instruments remain active on Voyager 1, the magnetometer, which measures magnetic fields, and the plasma wave subsystem, which listens to the charged particle soup the spacecraft is drifting through. Everything else, heaters, backup systems, redundant electronics, has been sacrificed piece by piece to keep those final instruments breathing for a few more years. Engineers at NASA's Jet Propulsion Laboratory have started calling their most ambitious power-saving plan the Big Bang, a coordinated swap of multiple onboard systems to squeeze out every remaining watt. They tested it first on Voyager 2, the twin spacecraft that took a different route out of the solar system, launched 16 days before Voyager 1, but arriving in interstellar space 6 years later. If the tests succeed, the same procedure gets attempted on Voyager 1. There is even a small chance that the low-energy charged particle instrument, already shut down, could be revived, its power channeled from somewhere else in the aging system. This is what keeping a 50-year-old spacecraft alive actually looks like. Constant triage, constant sacrifice. Engineers half a light day away making decisions about a machine they will never touch again, hoping each choice buys another year, another month, another data point from a place nothing else has ever measured directly. Every one of those decisions carries real risk, because a command sent to Voyager 1 cannot be undone once it is transmitted. There is no pausing halfway, no calling back a mistake. An engineer types out an instruction, sends it across a network of giant radio dishes, and then waits nearly a full day to find out whether it worked or whether it triggered a fault that could end the mission on the spot. In 2023, a single corrupted memory chip caused Voyager 1 to start transmitting nothing but meaningless gibberish back to Earth, an alarming, unreadable signal that left engineers unsure whether the spacecraft was even still functioning correctly. It took months of patient troubleshooting, of testing theories on the ground before ever risking a command to the real spacecraft, before the team finally identified the faulty chip and rerouted around it, restoring coherent communication. It was a small miracle of problem-solving performed on a machine older than most of the engineers who fixed it, using documentation written by people who, in many cases, had long since retired or passed away. That is the quiet reality behind every Voyager milestone, a small, aging team of specialists, some of the only people alive who still understand this particular spacecraft's original systems, keeping a nearly 50-year-old conversation alive, one careful, irreversible command at a time. And still, despite everything working against it, Voyager 1 is about to make history one more time. Sometime in mid-November 2026, on a date astronomers calculate slightly differently depending on their exact reference point, Voyager 1 will cross the one light day threshold. 25.9 billion kilometers, 16.1 billion miles. The exact distance a beam of light, the fastest thing in the universe, covers in 24 hours. No human-made object has ever been this far away. When that moment comes, a radio signal leaving Earth will not reach Voyager 1 for a full day. Its answering signal, traveling back at the same speed, will take another full day to arrive. A single ARU, end of communication, one question and one answer, now spans 48 hours. It took Voyager 1 just over 49 years to cross a distance light itself needs a full day to travel. Let that sink in. Light is instant to us. It crosses the room before you finish blinking. And it still needs an entire day to catch up with where this spacecraft has already gone. After that milestone, the story does not stop, but the countdown clock starts ticking louder. NASA's honest assessment is that Voyager 1 will likely run out of usable power sometime in the early to mid-2030s. Not a dramatic shutdown, no final catastrophic failure, just a slow managed fade. At some point, the last operating science instrument will no longer receive enough power to function, and the mission, in the sense of collecting new data about the universe, will effectively end. Even after that, though, the spacecraft T is not necessarily silent. Engineers believe that Voyager 1's radio transmitter, its most basic function, sending a signal, receiving a command, could keep working on residual power even after science instruments go dark. NASA has estimated that deep space network antennas could still track and communicate with a Voyager spacecraft through roughly 2036, depending on exactly how much power remains and how gracefully. The electronics continue to age. It becomes a race between physics and engineering. How long can you keep a whisper crossing billions of kilometers before there is simply nothing left to power the transmitter? Then, one day, there will be a final signal. Not a dramatic one. No alarm, no failure message, nothing cinematic. Just the last data packet Voyager 1 will ever send, arriving at a distille, Arnia or Spain, part of the Deep Space Network's array of giant radio antennas that have listened to this spacecraft for half a century. And then, silence. Not because the spacecraft stops, because it stops talking. Voyager 1 will not explode, will not fall, will not slow down. It will simply keep moving. carried by the exact same momentum it has had since 1980, coasting through the vacuum of interstellar space on a hyperbolic trajectory that requires no fuel, no power, no maintenance, forever. Losing power does not change a spacecraft's velocity. It only ends its ability to tell us about the journey from that T point forward. Voyager 1 becomes something new. Not a mission, but a monument. Humanity's furthest physical reach, drifting on, unreachable, unrecoverable, and utterly indestructible for all practical purposes, for longer than civilization has existed, for longer than our species has existed, for longer than most stars will exist. It is worth remembering what Voyager 1 is actually carrying into that silence. Bolted to its side is the golden record, a gold-plated copper disc containing sounds and images meant to represent Earth to whatever or whoever might one day find it. Greetings in 55 languages. Music spanning cultures and centuries, from Bach to Chuck Berry to traditional songs from cultures across the globe. Sounds of thunder, wind, a mother's kiss, a heartbeat. Photographs encoded onto the disc, a diagram of DNA, a sunset, a family sitting down to eat, human anatomy, our solar system with Earth marked as the only known home of life. Instructions on how to play the record are etched directly onto its cover, along with a diagram meant to help any potential finder locate Earth using the positions of pulsars, cosmic lighthouses that pulse at consus. The committee that assembled the record once described it as a message in a bottle cast into the cosmic ocean, an act of hope launched in an era when the odds of it ever being found were and still are vanishingly small. But Sagan understood something important. The record was never really for aliens. It was for us. A mirror held up to an entire species, asking what we would choose to say if we only had one chance to speak for all of humanity forever. That record, more than the instruments, more than the transmitter, is what will actually persist. Long after the plasma wave subsystem falls silent, long after the last deep space network dish loses contact, the golden record keeps orbiting the galaxy, sealed, against the near vacuum of interstellar space, essentially untouched by time in any way that matters to us. There is no oxygen out there to corrode it, no moisture to degrade it, no biological decay, no weather, no light pollution, nothing that ages objects on Earth. In interstellar space, a golden disk from 1977 can remain legible in principle for hundreds of millions of years, possibly longer. I well outlast every other physical trace of human civilization, every city, every book, every monument we have ever built. If some future intelligence ever comes across it, they won't be finding a functioning spacecraft. They'll be finding a fossil, a perfectly preserved snapshot of a species that existed once on a small blue world circling an unremarkable yellow star. Even the choice of what to put on that record was its own small drama. Sagan's committee had roughly weeks, not years, to decide what fragment of human experience deserved to represent the entire species forever. They argued over which pieces of music to include, whether to send images of war alongside images of peace, whether including detail. Human anatomy risked seeming indecent to a culture still uneasy about broadcasting the human body into space. They ultimately chose honesty over polish, images of scientists, farmers, families, cities, and wilderness, sitting next to sounds of laughter, a kiss, a mother comforting a crying infant, a rocket launching into the sky. It is easy to forget, watching Voyager 1's story unfold across billion-kilometer distances, that at its core this was always a deeply human project, made by people who understood they were building something meant to matter long after they themselves were gone. There is something almost unbearably poetic about the fact that the most enduring part of Voyager 1 will not be its cameras, or its transmitter, or its power supply, all of which were built for a project that originally expected to last a decade at most. The most enduring part is a piece of gold-plated copper the size of a large dinner plate, designed by a small committee working against an impossible deadline, meant to answer a question nobody had ever seriously been asked before. If you had to summarize an entire species in a way a complete stranger could understand with zero shared context, zero shared language, zero shared biology, what would you actually choose to say? But let's talk about the road ahead, because the timeline only gets stranger from here. Voyager 1 has already left the solar system in the sense that matters most. It crossed the heliopause, the outer boundary where the sun's solar wind gives way to the pressure of interstellar plasma, back in August 2012. It is now traveling through what astronomers call the interstellar medium, the vast, thin material that fills the space between stars. But it has not left the sun's gravitational influence, not even close. That boundary is much further out, defined by the Oort cloud, a theorized shell of icy debris that surrounds the solar system, extending outward in every direction. NASA projects that Voyager 1 will not finish crossing the Oort cloud, will not fully exit the sun's gravitational neighborhood for another 56,000 years. 56,000 years to finish leaving home. For comparison, 56,000 years ago, modern humans had not yet reached most of Europe. Neanderthals were still alive. Agriculture was tens of thousands of years in the future. That is the scale we are talking about, just to clear our own solar system's outer edge. And what happens after that is even stranger. In about 40,000 years, give or take a few thousand, depending on which calculation you trust, Voyager 1 will make its first close approach to another star. Not a visit, not a flyby in any dramatic sense, but a pass. The star is Gliese 4m45, sometimes cataloged as AC Pleasant 793888, a small red dwarf current. Lies sitting about 17 light years from our sun. Stars are not fixed points. They drift through the galaxy on their own paths. And Gliese 445 happens to be moving in our direction. By the time Voyager 1 arrives in that region of space, roughly 40,000 years from now, Gliese 445 will have drifted much closer, and Voyager 1 will pass within about 1.6 light years of it, closer to that star than our own sun will be at the time. 1.6 light years still sounds enormous, and it is, nearly 10 trillion miles. But in cosmic terms, that counts as a close encounter, closer than Proxima Centauri, our current nearest stellar neighbor, sits to us today. Voyager 1 will not be captured by Gliese 445's gravity. It will not enter orbit. It will simply drift past, silent, unpowered, unaware, a 50,000-year-old machine sliding through a stranger's solar system with nobody left to record what it sees. That will not be its last encounter either. According to research on the long-term trajectories of spacecraft leaving the solar system, an object on Voyager 1's path will statistically pass close to a star roughly once every 50,000 years, simply because that is how frequently stars pass near each other as they all orbit the galactic center. Multiply that rate across a timeline of trillions of years, and Voyager 1 is going to have a lot of neighbors. In about 570,000 years, it is expected to brush past two more stars, cataloged as GJ 686 and GJ 678. Around 5 to 6 million years from now, it should exit what astronomers call the local bubble, a vast, sparse cavity in the interstellar medium, carved out by ancient supernova explosions, a region our entire solar system currently sits inside. Beyond that point, predictions get genuinely uncertain, because scientists still do not fully understand the long-term motion of interstellar dust clouds and rogue, starless planets that might drift through, unseen, until they alter a spacecraft's path with a gravitational nudge nobody could have predicted from Earth. Zoom out even further, and Voyager 1 stops being a spacecraft with a trajectory and starts being a body with an orbit, just like a star. Every star in our region of the Milky Way, including our sun, is orbiting the galaxy's center, completing one full loop roughly every 225 to 250 million years. Voyager 1, no longer meaningfully influenced by the sun's gravity, effectively becomes its own independent object doing the exact same thing, circling the galactic center again and again for hundreds of millions of years on a slow, steady orbit through the Milky Way. Voyager project scientist Ed Stone once put it plainly: the spacecraft will keep completing that galactic orbit for billions of years, until some future collision disrupts the pattern. And here is a collision scheduled. In roughly 4 billion years, astronomers expect the Andromeda Galaxy, our closest large galactic neighbor, currently racing toward us at about 110 kilometers per second, to collide and merge with the Milky Way. Individual stars almost never collide directly in a galactic merger. The distances between them are simply too vast. But gravity gets rewritten, orbits get scrambled, and somewhere in that chaos, Voyager 1, this tiny 50-year-old artifact, keeps drifting, indifferent, unaffected by the scale of the event happening around it. Because nothing about a merging galaxy can meaningfully touch an object this small moving, this vast through space, this empty. What eventually destroys Voyager 1, if anything ever does, remains genuinely unknown. It could be death by 1,000 tiny impacts, micrometeorites chipping away at its structure over unimaginable timescales, slowly sandblasting the spacecraft down to nothing. It could be one improbable, catastrophic collision with something larger, a rogue planet, a dense cloud, a piece of interstellar debris crossing its path at exactly the wrong moment across a journey spanning billions of years. Or, and this is the possibility, that should genuinely unsettle you, it might survive essentially forever. Space, real interstellar space, is so overwhelmingly empty that the odds of Voyager 1 hitting anything of consequence ever are staggeringly low. It is entirely plausible that this piece of human engineering, dead, dark, and silent, could keep drifting through the galaxy for longer than the galaxy itself has existed in its current form. A ghost ship with no captain, no destination, and no expiration date. Now here is where the story stops being about a spacecraft and starts being about everything. Because Voyager 1's future timeline does not exist in isolation. It exists inside the much larger, much stranger timeline of the universe itself, and that timeline is the real reason this story earns the number 10 trillion. Right now, cosmologists divide the life of the universe into distinct eras, and we happen to live in the second one, called the Stelliferous Era, the Age of Stars. It began roughly 1 million years after the Big Bang, once the early universe had cooled enough for the first stars to ignite, and it is expected to continue for roughly 100 trillion years total. We think of stars as permanent, as the backdrop to everything, but they are not. They are temporary. Every star is slowly converting hydrogen into heavier elements through fusion, and every star eventually runs out of fuel. Massive stars burn fast and die young, in cosmic terms, lasting only millions of years before exploding as supernovae. But the smallest, coolest stars, the red dwarfs, the same category of star as Gliese 445, burn their fuel so slowly and so efficiently that they can keep shining for trillions of years. Astronomers estimate that the very longest-lived red dwarfs will not begin burning out until roughly 10 trillion years from now. 10 trillion. The same order of magnitude. The same almost incomprehensible span of time that gives this story its title. Try to actually picture 10 trillion years, because your brain will resist it, and that resistance is the point. The universe, right now, is about 13.8 billion years old. Multiply that current age by roughly 700, and you get somewhere close to 10 trillion years. Human civilization, agriculture, writing, cities, all of it spans roughly 10,000 years. 10 trillion years is 1 billion times longer than that. It is a span of time so vast that comparing it to anything in human experience is functionally meaningless. There is no analogy, no scale model that makes it intuitive. And yet, it is a real number, calculated from real physics, describing a real future that is, in principle, going to happen, whether or not anything remains to witness it. By the time we reach that 10 trillion year mark, almost everything familiar about the universe will already be gone. Long before then, within just the next couple of trillion years, the accelerating expansion of the universe, driven by the mysterious force cosmologists called dark energy, will have pushed distant galaxies so far away that their light can no longer reach us, ever, at any speed, because the space between us is expanding faster than light itself can cross it. Future observers, whoever or whatever they might be, looking out from the Milky Way at that point, would see only their own galaxy and a scattering of nearby, already merged neighbors, surrounded by pure black nothing. They would have no evidence the Big Bang ever happened, no evidence of expansion. They might reasonably conclude their static, silent galaxy has simply always existed exactly as it appears, unaware that they are living in the faded afterglow of a much larger, much richer cosmos that expanded itself into invisibility. Around 100 trillion years from now, the last new stars will form, and star formation itself will end permanently, because the raw hydrogen and helium gas needed to build new stars will finally, completely run out. That marks the true end of the Stelliferous Era and the beginning of what astrophysicists call the Degenerate Era. In this new age, there are no newborn stars, only remnants, white dwarfs, the slowly cooling cores left behind by stars like our sun, neutron stars, the ultra-dense husks of larger stars that exploded, and black holes, the crushed remains of the most massive stars of all. Even galaxies themselves begin to fall apart during this era, their stars gradually flung outward or pulled inward by chaotic gravitational interactions accumulated over unthinkable spans of time, until galactic structure as we understand it simply dissolves. And this is where Voyager 1's story and the universe's story finally converge into the same frame, because if this spacecraft somehow survives, uneroded, undestroyed, adrift in the vast emptiness between what remains of stars, it will still be out there when the last red dwarfs, the toughest, most fuel-efficient stars in existence, finally exhaust their hydrogen around that 10 trillion year mark. It will still be out there as those final embers of starlight flicker and fade to black, one by one, across a universe already unimaginably old, unimaginably dark, unimaginably empty. Voyager 1, launched by a species that, by then, will have existed for less than a rounding error of the universe's total lifespan, could plausibly be drifting through that darkness alongside the very last stars in existence. A tiny, cold, golden-plated artifact outlasting the light itself. Beyond even that lies the black hole era, a period cosmologists estimate stretching from roughly 10 to the 40th years out to 10 to the 100th years, numbers so large they cease to represent anything countable, in which black holes become the last organized structures left in the universe, slowly evaporating through an extraordinarily slow quantum process theorized by physicist Stephen Hawking, radiating themselves out of existence one particle at a time, over spans of time that make 10 trillion years look instantaneous by comparison. After that, Cosmologists describe a final, near-total stillness they call the dark era, a universe of cold, diffuse radiation and drifting particles, expanding forever, with no stars, no light, no structure, nothing left to do but exist, thinly and quietly, essentially forever. Think about what that actually means for an object with no engine, no pilot, no destination. Every other human-made thing that has ever traveled through space had a return trip planned, or crash planned, or planned decay back into Earth's atmosphere. Satellites eventually fall, space stations eventually burn up. Even the footprints on the moon, protected from wind and rain, are expected to erode slowly under 1 billion years of micrometeorite bombardment. Voyager 1 has no such expiration built into its design because nobody designing it in 1975 was thinking past a decade, let alone past the death of the last stars. It simply kept going past every deadline anyone ever set for it. And it will likely keep going past every deadline the universe itself eventually sets, too. There's a strange kind of accidental immortality in that. Nobody chose it. Nobody engineered it. It happened because the emptiness of interstellar space is simply so complete, so overwhelmingly free of obstacles, that a slow-moving chunk of aluminum and gold-plated copper can, in principle, just keep drifting, unbothered, for longer than anything else humanity has ever built. We will never know how any of this plays out. No human, no civilization built by humans, no descendant species we could recognize will exist to see it. That is not pessimism. It is simply math. The same kind of math that tells us Voyager 1 needed 49 years to cross a distance light crosses in a day. But the spacecraft itself does not need us to witness anything. It does not need consciousness, or purpose, or an audience. It only needs momentum, and it has had that, unbroken, since 1980. So somewhere out there, right now, while you have been listening to this, that 23-watt machine is still falling silently through interstellar space, carrying a golden record of human music and human voices toward a future none of us will ever see, toward stars that have not been born yet, past stars that will not die for trillions of years, into an era of the universe that does not have a name yet because nothing has survived long enough to need one. It left Earth in 1977 to study 2 planets. Instead, it became the longest story humanity has ever told, one that started with a rocket launch from Florida and will not finish, if it ever finishes at all, until long after the last star in the universe has gone dark. And maybe that is the real reason this story is worth telling now, while we can still hear it speak, while its faint 23-watt whisper still reaches home. Because one day, not too far off, it will stop answering us for good, and everything that happens to it afterward will unfold in a deep, permanent silence that lasts trillions upon trillions of years, witnessed in the end by no one at all,